In this video, we're going to be continuing what we did in the last and discussing the Quantum Fourier Transform. In the last video, we talked about this transformation over the field of integers mod 2 to the power of n. So these are like n length bit strings. And in this video, we're going to talk about the Quantum Fourier Transform over the integers mod n. So this is the set 0 all the way to n minus 1. And the addition operation is mod n. And the idea is going to be like essentially the same thing. We are going to take a function that maps this set, Zn, to the complex numbers, and we want to decompose it into like linear combinations of some other pattern function. So we want to decompose G into, which we'll call each of these pattern functions, we'll call them chi, similar to what we did in the last video. And there's going to be n minus 1 of these. And each of these is a function similar to G, from Zn to complex numbers. And what these functions are going to be are essentially what we'll call discrete cosines. So these are discrete sine and cosines. So these are like sine and cosine functions, but they are only they have as input discrete values, and they map to discrete values. So just as a remark, so we can think about the difference between what we did in the last video. In the last video, we were taking functions mapping f2 to the n, which is just the integers, or 0, 1 raised to the power n, going to the complex numbers. We took these functions and we decomposed them into these other pattern functions, which I'll just call them chi again, indexed by some subset of whatever bit string and taking as input another bit string. And in this case, what the function ended up being was -1 raised to the mod 2 inner product of these two things, s and x. In this case, our pattern functions are going to look a little bit different. What they're going to be is for chi of s acting on x, it's going to be the nth root of unity raised to this product between s and x. And unlike in this case, where this was like the mod 2 inner product, this is going to be just the normal product of two integers. And one thing to note is that even though this is the normal product, since this is a root of unity, the only thing that matters is the value mod n. And just to remind ourselves, the nth root of unity is e to the 2 pi I over n. So this value here is going to be e to the 2 pi I s dot x over n. And now we want to continue the same way we did when we were working mod 2, and associate each of these functions to a vector. So we want to take a function g and come up with a vector that represents this function that will also be a quantum state for us, because this is the quantum Fourier transform, so we want to come up with a unitary that acts on quantum states. So we'll associate this ket g to the following function. And we're just going to add this normalization factor to make things easier. And this is going to be the sum from x equals 0 to n minus 1, where each of the amplitudes are just the function's value on that particular basis state, which just represents an integer here. So the x's here, the ket x's, are just the standard basis vectors. So for example, 0 is just 1, and then 0 is everywhere else, and you get the idea. Yeah, so this is a quantum state, if and only if. So a quantum state, if and only if these sums of the squares of all the amplitudes is equal to 1. And since each of these already, we pulled out this factor of 1 over the square root of n, we have that 1 over n, and then sum over all these g amplitudes squared, this is over all x, is equal to 1. So what we want the QFT, the quantum Fourier transform, to do is take a state like this, G, and then map it to a linear combination over these chi's. So in this different basis, the chi basis. And here we have the sum over S with this G hat S, which is like the Fourier coefficient of the S chi function. And what G hat S ends up being is just like the projection of our original G onto this particular pattern function. So this is just like the standard way to come up with a unitary that maps from one basis to another. And the basis of interest for us is the ones made up with these chi's. Oh yeah, and so ket chi is different than chi on its own because we have to do this standard quantum standard way we associate a function to a quantum state. So this is just 1 over the square root of n minus 1, x equals 0, chi of s, x on x. And from what we have above, this is the root of unity, the nth root of unity. So this is the ket chi of s. So yeah. So before we go further, we want to show that these chi of s's actually form an orthonormal basis so that we can justify everything that's happening here. And in order to do that, I'm just going to write down a few properties about these chi of s's. And I'm not going to prove them, but they're all relatively straightforward. And you could easily convince yourself that any of these are true. So the first thing I'll say is that chi of 0 on x, or actually I can just write chi of 0 here. This is just the 1 function. So it's identical to just 1. So chi of 0 on any x is just equal to 1. This is because this is equal to e to the 0, which is equal to 1. And another thing is these are complex numbers. So it's good to understand what happens when we take complex conjugates. And here, if we take a complex conjugate of this particular value, we take the complex conjugate of the root of unity, and all that happens is we get a negative sign in the exponent. So this can be rewritten as chi of minus s x. And another thing that is kind of neat is that it doesn't really matter the order of operations we do for s and x here. So in particular, chi of s on x is equal to chi of x on s. And another thing that we get out of this, the fact that we're using the exponential function, is that we turn multiplication of these Fourier characters into addition on their inputs. So this is easily checked, but the property is chi of s on x times chi of s on y is equal to chi of s on x plus y. So that's pretty nice, and that's going to help us prove the next thing, which is that these guys are orthonormal. So in particular, chi of 0, chi of 1, all the way to chi of n minus 1 are all orthonormal. So let's prove this. We'll prove the harder part first, which is the case where we have two different chi functions. So in order to prove orthonormality, we have to show that two different chi functions, if we take their inner product, it's going to be 0. And for two of the same, it's going to be 1. So for s not equal to t, we want to compute this guy over here, chi of s, or chi of t, chi of s. And here we use the standard inner product on quantum states, which is just to multiply all their amplitudes entry-wise and add them all up. And these just end up being the actual function values of the original chi's. So this is going to be, and remember for the bra notation, we have to take the complex conjugates of all the amplitudes. So this is going to be the sum. And since this thing is going to evaluate to 0, I'm just going to ignore the normalization for now. It doesn't really matter. We have the sum from x equals 0 to n minus 1 of chi of t complex conjugated x, chi of s, x, and here what we can do is use our properties up here, in particular this one and this one, and we write, firstly, this is equal to n minus 1, x equals 0, chi of minus t, x, chi of s, x. And now we do the flip for x and t and x and s, and we get this. And now we use this neat property where we can turn multiplication into addition. And this gives us this pattern function, s minus t. And now we just write this in terms of what it actually is, which is the nth root of unity to the power of x times s minus t. And we know that s and t are different. So in particular, s minus t is equal to some value k, which we know is not equal to 0. And that's all that really matters here. So we say this thing is equal to the nth root of unity to the power of x times k, which is this exactly, 2 pi I x times k over n. And now we can simply use the formula for the sum of a geometric series, and we'll quickly see that this thing is equal to 0. So the sum, and I'll just use big N here, is equal to, or the sum from the first term to the nth term is equal to the first term times the ratio between the terms, minus 1, or the ratio to the power of n, and then over the ratio minus 1. So here, our first term is when x is equal to 0. So e to the power of 0 is just 1. Okay, so it's easy to see that at each step of this sum, the term that we're adding increases by a factor of e to the 2 pi I times k over n. So in particular, r the ratio is going to be e to the 2 pi I k over n. So now we actually know everything to plug in here. And this sum is actually only for the case where r is not equal to 1. So when r is equal to 1, things change here, obviously. And in this case, r is clearly not equal to 1. So here, what we get for the sum is going to be just 1 for a1, so nothing there. And then e to the 2 pi I k over n raised to the power of n. So that's just going to get rid of the denominator in that exponent. So this is 2 pi I times some non-zero k minus 1. And we actually don't even need to look at the denominator. All that matters is that the denominator is not 0, because this numerator is actually 0. So in particular, this value here is always equal to 1. Every multiple of 2 pi I just takes you back to 1. So this thing is going to be 0. And we've proved the first thing here. So now for the second thing, for s is equal to t, we want to compute this value, chi of s on chi of s. And here we annoyingly have to remember the normalization constants because we want to show this thing is equal to 1. So what is this thing going to be? Well, it's going to be a sum from x equals 0 to n minus 1 of chi of s of x conjugate transpose, or just conjugate because it's a complex number, times chi of s of x. And then from our identity, we know this is minus s. And then we know this is x minus s. And this is xs. And then using the conversion from multiplication to addition, this thing is chi of, I said we need to remember the normalization constants, and we do. So this thing is going to have 1 over square root of n times 1 over square root of n, which is, of course, just 1 over n. And then again, using our conversion from multiplication to addition, we have chi of x acting on 0, and we do the same flip. And this thing is just equal to the 1 function. So we just add 1 n times and then multiply by 1 over n. Of course, that's equal to 1. So these guys are orthonormal. Let's see what's next here. Yeah, so now this is kind of the cool part, also the somewhat difficult part, is we want to show that there's actually a fast implementation of this unitary transformation on a quantum circuit. Because that's the whole point. Like, this is supposed to be something that's going to allow us to compute things efficiently. So it'd be really nice if there was an efficient way to actually construct this unitary. So now we're going to show how you can implement QFT for some particular n with n times n plus 1 over 2 gates, which is less than n squared. And yeah, and sorry, only 1 and 2 qubit gates here. Okay, so we're gonna do this for a small example, and this should be enough to give the idea of how this circuit's constructed for any generic n. Everything is pretty much captured in this example. So we want to do it for little n equal to 4, which is going to give big N equal to 16. It's going to be 2 to the power of 4. And just to remind ourselves, what is it we really want to do? We want to take, for example, it's enough to define this action on a basis. So we'll choose the computational basis. We want to take some integer value, some computational basis number x. And when we apply this unitary, QFT 16, we want to get 1 over the square root of 16. And then the sum from s equals 0, chi of s, x, conjugated, summing over all these basis states. And I realize in my notes here, I may have mixed up the inverse quantum Fourier transform and the forward version. It's really not too important, but I guess, so this is the forward way. And I guess the idea is some basis state x is already has some representation in the chi basis, and our goal is not to take it to the chi basis, but take it back to the standard basis, which is why we have these standard basis vectors up here and up here. When I first defined the transformation, I wrote it this way with the chi basis here. So I guess this is probably the inverse Fourier transform. So this is taking something from the standard basis to the chi basis, but we want to take it back to the standard basis with our coefficients being these chi values. Yeah, it's really not too important. The actual unitary matrices end up being pretty much the exact same thing. I mean, in particular, because this thing is unitary, it's just the conjugate transpose of one another. But this is the transformation we want because we want to measure in the computational basis and actually obtain some information about these coefficients. Like this is when we actually want to run this thing to compute something for us. So this is the transformation we're looking for. Yeah, so how are we going to do this? Well, it's helpful to write this thing out explicitly. So in particular, this thing over here, this chi of s on x, is going to be the 16th root of unity for s dot x, and then conjugated. And when we conjugate this thing, we know we're just going to add a negative sign in the exponent. So there's going to be negative s dot x 16. And we know everything is the 16th root of unity, so I'm just going to drop this notation now. So this is what we're going to write. And QFT 16 acting on x is going to be this. Like we're going to rewrite this sum here, but expand it out fully. 1 over root 16, which is just 4. And then for the first computational basis state, it's going to be 4 qubits, all zeros. And we're going to have the 16th root of unity to the power of 0 times x conjugated, which is just 0, which is just 1. And then continuing this and using our formula, we're going to have for the first computational, or the second, minus x here. And then for the third, minus 2 times x for the bit string representing 2. And you get the idea. And we take this all the way down to 15. which is the largest number we can represent with 4 bits, minus 15 times x. And there's like a really nice property about this whole thing, which like seems like a coincidence, but it's kind of beautiful and it helps this whole thing work out. And it's that this thing is actually a product state of each of the qubits. So that's not like super obvious at first, but yeah, this is something that's true. And I'll show you. So this is a product state. In particular, it's this product state. So for the first qubit, it's going to be 0 plus the 16th root of unity to the power of minus 8 times x, 1 over root 2. So it's this superposition. And then the second qubit is in a similar state, but we have, instead of minus 8 times x, we have minus 4 times x over root 2. And I'm just going to move this down really quickly. Oops. And then for the last 2 qubits, we do the same thing and we just cut it down again by a factor of 2. Oh, this is a minus sign here. Minus x. Okay, so now let's see why this product formula is actually equivalent to this sum that we wrote up here. So in particular, we want to show that this thing is a linear combination of basis states, which we'll index by s, of the 16th root of unity to the minus x times s of s. So one thing to take note of is that for each term in this sum, we encode it into the exponent of this root of unity. And let's examine this thing bit by bit. So here, just writing out the exact same thing, but splitting it up into the different bits. We have the most significant bit, followed by the lesser significant bits. And if we want to obtain the base 10 value of some binary string, we can use this formula. So this is the formula for bit strings of length 4. We have 8 S3 plus 4 S2 plus 2 S1 plus S0. So this is the value we have in the exponent in terms of the actual bits, because we want to look at this thing bit by bit, which is what's happening here with this tensor product. So let's just expand this further and split this up into a product of different phases. So what we have is this first portion, followed by this thing for the second most significant bit, and then the third most significant bit, and then lastly the least significant bit. Okay. So now let's see what actually happens looking at this product formula if we were to expand it. So it's clear, first of all, that we are going to get some linear combination of all the computational basis states from the all zeros to the all ones for 4 qubits. But the question is, what amplitude is going to be associated to each basis state? So let's consider, and we'll just keep using this S notation. Let's consider some S prime, which is S prime 3, S prime, and I'm going to actually split this up into its tensor factors. S prime 2, tensor S prime 1, tensor S prime 0. So if we were actually to expand this product, we want to ask what's the amplitude that's going to go here. And we can do this by looking at the amplitude that's going to go in front of each of these things separately, and then just multiply them together. Because this thing, all of this represents the most significant bit. This is the second most, and so on. Okay, so let's go ahead and do that. So for the first most significant bit, S prime 3, we have this term here. So what we want is, if S3 is going to be 0, then we don't want any amplitude. Now, if S3 is 1, then we want to add this root of unity to the minus 8x. So it actually depends on the value of S3. And we can encode this not as actually splitting up the cases, but by just putting the bit value into the exponent, because that will kind of control whether or not we actually apply it or not. So in particular, in front of S3 here, and let me move this over here. So in front of S3, what we're going to have is the 16th root of unity to the minus 8 times x, or minus 8x, and then conditioned on the actual value of S prime 3. So this sort of, you can just like think it out for yourself. So if S prime 3 is 1, then we add this phase. And if S prime 3 is 0, then we don't add any phase. And that's exactly what we were looking for. Okay, so now we're just going to do the same thing for these other guys. Oops. Let me just make some space here. Okay, so we can, I don't really have to even write all this out, but I might as well. Doing the same thing for S prime 2, we get a conditional amplitude of omega to the minus 4x. So again, we encode that conditioning by putting S prime 2 in the exponent and just continuing this. And when you have a tensor product like this, these scalars just multiply. So this is obviously going to give us this thing we had up here for any particular value of S. Okay, so now that we've like validated that this product formula is actually correct, we can start thinking about the actual quantum circuit that's going to implement this. So let me just move this down. So we want to come up with a quantum circuit. It's going to take 4 qubits, x1, x2, x3, x4. And this thing is going to map to a different set of, or the same set of qubits. But here I'm going to swap the order of significance. And this is just going to make things easier in the end. So S4 is going to be the most significant bit here. And at the start of the circuit, X4 is going to be on the bottom, and then the most significant bit's going to end up being on the top. And it doesn't really matter. You can apply like a permutation gate here to fix that. Oops. So you can apply some like permutation that just reorders all of these, but we're not going to worry about that for now. So let's first take a look at this this first guy here. So we know X is just X4, X3, X2, X1. And the actual value of X, like expanding the binary notation, is 8 times X4 plus 4X3 plus 2X2 plus X1. And we want to take X, or X1, and put it into a superposition where the phase on the 1 state is the root of unity to the power of minus 8 times X. So we need to actually like account for what value of X we have here. So that what might make you think that like we might need 2 qubit gates connecting X1 to all the other qubits so that we can account for this full value of X. But it turns out we actually don't need to do that. And the reason why that is very nice. And it's because we actually only care about X's value mod 2. So this thing is, again, expanding in this notation, 8x4 plus 4x3 plus 2x2 plus x1. And then recalling that the root of unity here is e to the 2 pi I over 16, we get that this thing is e to the negative pi I times this value of X. And I'm arguing that we only really care about this value. So why is that? Well, in each of these other cases, we're adding a multiple of 2 pi I. And we know that e to the negative 2 pi I is just equal to 1. So all of these actually just cancel out. So this thing ends up being equivalent to e to the negative pi I times x1. And e to the negative pi I is just negative 1. So the transformation we want on the first qubit is x1 going to 0 plus negative 1 x1 over the square root of 2. And we actually already know a gate that does this. It's just the Hadamard transform. So we know what our first gate is going to be on the first qubit. It's going to be just a Hadamard. And I'm going to put it at the end here because we still want to use the value of the first qubit to decide what gates we're going to put on the other ones. And we want the initial value, not the value after the Hadamard. Okay, so moving on. Let's take a look at the second qubit. We want to go from x2 to 0 plus the 16th root of unity to the power of minus 4 times x. This is the thing that we want. So now let's do a similar thing. So plugging in the value for w again, we get that this thing is e to the minus pi I over 2 times x. And remember, x is 8x4 plus 4x3 plus 2x2 plus x1. And here, again, we're going to do like a similar thing. But in this case, we don't only care about its value mod 2, we care about its value mod 4. So the only actual bits that are going to contribute to that are these guys. And the reasoning is the exact same. Multiplying this value here by 8 and by 4 is going to add multiples of e to the minus 2 pi I. And that's just going to cancel to 1. So this thing is e to the minus pi I 2, 2x2 plus x1. And what is this? This is writing it as a product. We have e to the minus pi I x1 over 2 here. And simplifying further, we have minus 1 to the x2 and minus I to the x1. Okay, so rewriting what transformation we want exactly. We want to take this thing into 0 plus minus 1 x2 minus I x1 1. Okay, so we're going to do like the first step. So we're going to split this up into 2 steps. First, we're going to apply a Hadamard onto the second qubit. So that's going to get us like almost there. So applying a Hadamard, we have 0 plus minus 1, and we're doing it on the second qubit, so we get this. Oh, sorry, not 0. We want x2. Yeah, so applying a Hadamard on the second qubit gives us this over root 2. And now we want to just sort of add a phase gate conditioned on the first qubit. So we want to take a state like this and take it one step further and just add a particular phase. As I'm running out of space, let me just rewrite this down here. Oops. x1. Okay. So how are we going to do this? Well, this is like a phase, but conditioned on the value of the first qubit. So if x1 is equal to 0, then do nothing. And if x1 is equal to 1, add phase negative I. So I'm just gonna like sort of invent this gate for us, and just try to argue that it's like natural enough that there is an easy way to implement this. And the way I'm going to argue that is just to say this is like very similar to a gate we already know, not control not, like it has that similar control structure, but it's very similar to control Z. So this is like, this control not is like CX. Control Z is like we're applying a phase of -1 conditioned on the control qubit, which in this case is x1. But instead of doing that, we don't want to add a phase of -1. We want to add a phase of -I. So that's like control root Z, which is pretty cool. And there's a way we can do this. And I'm just going to assume that we can, because we can. So again, the first thing we did was Hadamard. And the second gate we want is conditioned on the first qubit, adding a root of unity, 16th root of unity to the minus 4, which is just minus I. Okay, so now let's continue to the third qubit, and then after the third qubit, things will be clear enough, and we can just quickly generalize to what the last qubit's going to look like. Okay, so what do we want for the third qubit? We have x3, and we want to take that into 0 plus minus 2 times x, 1 over root 2. And similar to the previous things, this value, we actually only care about x mod 8 here for the exact same reasons. So what is this? 4 pi I over 16, which is just pi I over 4. 8x4 plus 4x3 plus 2x2 plus x1. So if we only care about this value mod 8, then we don't care about this qubit. We only care about these guys. Okay, so we're just going to distribute everything in this product in the exponent. Now knowing that we don't need this x4 bit, so what we have is e to the minus pi I x3, e to the minus pi I x2 over 2, and then this thing. And just to simplify things for us, we can rewrite this. And then here we have minus I. And then here I'll just keep it in its root of unity form. So this is, what is this exactly? So the 16th root of unity raised to the power of 2. Yeah, 2 or minus 2. x1 here. And so this is essentially the phase that we want. So we know we want to make the transformation from x to this superposition. And this is, normalized by root 2. And there's also a ket here. So we, not x, 1. So we want to enact this transformation. So we're going to proceed how we did with the previous one. And we'll observe that we can get the first part of this phase just through a simple Hadamard. So the transformation we know is going to start with a Hadamard. And then we want to add this second phase. Oh, and this Hadamard is specifically on the third qubit. And now we want to add this second phase conditioned on the second qubit. So the control qubit here is going to be the second qubit, and the target is going to be the third qubit. And remember, this controlled minus I is like a controlled root z. So I'll just write it this way. But root z here, this minus I, just to keep everything actually consistent, I can write this as a controlled omega to the minus 4, where omega is the 16th root of unity. And then just to specify the control and target bits here, we have the control bit is 2, and the target bit is 3, or qubit. And then similarly for omega to the minus 2, our control bit is now going to be the first qubit, and the target qubit is going to be still the third. So the addition to the circuit is going to look like this. So now we'll just go back up to the circuit. Where is it? Over here. And draw this thing. And remember the order that we have to draw it in. So the Hadamard is going to come first. It'll be like around here to give ourselves enough space. And then the next thing we're going to have to do is this omega to the minus 4, which is similar to what we had up here. And then lastly, omega to the minus 2. And now I could proceed for the last qubit, but I think from here it's pretty easy to see the pattern. So we'll just go ahead and write it down. So the last thing is we're going to first have this this controlled root of unity going from the first qubit to the current qubit that we're on, which is the fourth. And then each time this thing goes down by a factor of 2, so this root of unity is going to be raised to the minus 1. And then, oops, not there. The next gate is going to be controlled by the second qubit, which is going to be this omega to the minus 2. And then this final 2-qubit gate is going to be omega to the minus 4. And I'm running out of space here. Let me just give myself some more space. And then the last thing here is just a Hadamard. So this is what the circuit looks like. And in the process, we like swapped the order of the bits here in terms of their like significance. And so there's some conventions where you just do a permutation gate here to permute these guys. But it's really not important. This is the idea. This is the Quantum Fourier Transform. And let's quickly count the number of gates that we use in terms of n, little n, the number of qubits, just to verify that we did it in less than n squared number of gates. So ignoring this permutation gate, for the first qubit, we only have one gate acting on that qubit, where it's not like the control for a different gate. So that's 1 for the first qubit. And then for the second qubit, it's 2. For the third, it's 3. And for the fourth, finally, it's 4. So it's 1 plus 2 plus 3 plus 4. And it's easy to see, like if we had n qubits rather than 4, the sum would continue to n. And this, of course, there's a formula for this, and it's n times n plus 1 over 2, which is less than n squared. So this thing can be implemented efficiently on a quantum computer, which is pretty neat. So in the next video, we're going to see an application of this transformation to do something similar to what we saw with Simon's algorithm. There's going to be some function we want to implement, f of x, and it's going to have the property that it's periodic. And this time it'll be periodic with respect to normal addition rather than binary addition. And we're also going to be given access to this unitary that's going to implement this function for us in the standard way. And the goal is to come up with some quantum circuit such that we make a minimal number of calls to this unitary u of f, such that we can determine what L is. And we'll see that that's going to require the quantum Fourier transform. It's going to be really useful for that. And this ends up being really the heart of Shor's algorithm, which we'll get into in future videos. So, yeah.